Okay, welcome back. We're about to do some questions from this worksheet that you'll find in the link in Compass. It's dynamic worksheet 4B and it is on the inclined plane, but this time we're doing frictional parts of the force. So let's just work a few things together, then I'll let you go on and then we'll come back and have a look at some of the harder ones towards the end. Okay, so the first one we're going to do is a vehicle of 1,850 kilograms is parked on a frictionless slope at an angle of 15 degrees. What force is being applied by the brakes? So let's just analyze this question. We've got a slope here, and here is our little vehicle, and normally there would be a force pulling down. Well, not normally, but there is a force going down there, and that is, as we know, mg sine theta. And so there is a force of friction up here. Now, this frictional force is actually the brake force. So that's the braking force up there. So that would equal, question one, that the force that of the brakes is equal to mg sine theta. So this is very similar to the questions that we've already started with at the end of the previous worksheet. So I'm not going to go any further with that, but if you need any more assistance, please email. Going on to question 2, a 15 kilogram mass is stationary on a plane and it's at 23 degrees to the angle. What is the magnitude of the frictional force? It is identical to this question 2. So the frictional force in this case is equal to the force down the plane. So ticking those two. Excuse me. Question 3 now. Question 3, SeaWorld, a polar bear is sliding down a wet slide at an angle of 25 degrees. So we're assuming that the slide is like that, and here is our polar bear. Okay, I'll put some polar bear legs and arms on. Okay, and a nose. Rightio, it's a very cute polar bear. And it's sliding down. Now, the coefficient between the bear and the slide is mu equals 0.05. Now, because it's sliding down, this would be mu k. Okay, what is the frictional force that on the bear? Okay, so we know that friction is equal to mu k n, and n is mg cos theta. So in this case here, it's very simple to work out that this will be mu naught, which is 0.05 times mg cos theta, where m is the mass of our polar bear and theta is the 25 degrees. Okay, moving on again. 4. Question 4 has a mass is stationary on an inclined plane. When the inclined plane is increased to 38 degrees, the mass begins to move. So what is the coefficient of static friction? Well, from our theory that we've already done, we know the coefficient of static friction is equal to tan of the angle that makes the object first move. So you're going to use that in this question. So you'd simply work out that theta, that's actually what we're just about to use. Okay, so use that one to answer this question. Moving on to question 5. Question 5, the angle, once again, of an inclined plane can be varied. The surface of the plane has a coefficient of static friction of 1.2. What angle would need to for a 5 kilogram mass to slide down? Once again, you're going to use that result there, that mu s is the tan of the angle of the static friction. Okay, moving quickly along these ones here. So this is just to help you along. So 6, a 2.5 kilogram mass rests on a horizontal surface and has to be pushed with a force of 12 newtons before overcoming friction. It begins to move. At what angle would the surface have to be inclined before the mass would begin to slide under gravity? So this one here is giving us an idea that if we've got a horizontal surface, then this force is the frictional force that is needed, that's the static frictional force, would be equal to the driving force here. Okay, so we know that on a horizontal surface, force of static friction would equal normal times, so just do that again, it'll be mu s times n. Okay, and n on a horizontal surface is equal to mg. So it'll be mu s times mg. Okay. So this enables us to work out what mu s is, because we know that this here is 12 newtons. So mu s would equal 12 divided by mg. Now we've got mu s, we can use this up here, that mu s is equal to tan of the angle that you will incline the plane to before it first moves. Okay. And finally, for question 7, you are going to be doing the same thing again, except in this one a coefficient of kinetic friction. So we've got an object here which is already in motion moving down, but it's at a constant velocity. So in this case, if it's moving down, its acceleration down would be the force down would be mg sine theta, and the motion up would be friction. Now, if they are equal and this was stationary, this would be static friction. But because this time they're equal, but it's actually in motion, it's kinetic friction. So it's a different value. Okay. Once again, it's exactly the same. The force of kinetic friction is mu k times n, and n is still mg cos theta. Okay, so we know that mg sine theta is equal to mu k mg cos theta, and they cancel. So once again, you get mu k, just moving that up again, mu k is equal to tan theta. So we get both things as mu s, that's this static friction one, is equal to tan theta, and that's the angle at which it first moves. We get mu k equaling tan theta, and this is the angle that it slides down at a constant speed. Okay, so that's the only difference between these two values here. So that's question 7. Okay, I'll post a video doing 8 and 9 next. Thank you.